the sort of changes we've seen in the physics representation of games over time. So I'll start with a little story. Once upon a time, game engines didn't actually have any physics engine. So we're all now used to some sort of rigid body physics simulation in our game engines, but they didn't. So a wooden crate back in the day was just a box. A ball might have had a monkey in it, but it was still represented as a sphere. So the graphics and the physics, the representation of each was pretty much the same shape, except when you started to get into things like barrels, or spheres and boxes and barrels and crates, standard physics demos. But a rusty barrel would have been represented by a single box primitive so that it could be stood on its end, and maybe two sphere primitives, implicit spheres and implicit boxes, so that it could roll nicely down the hill. So we've actually started quite early on to get divergence between the representation of the physics and the representation of the physics, or of the graphics, sorry. Now, I was a user of Havok before it was called Havok. It was originally called Omniad. And back then, while there was a rigid body simulation as part of the Omniad SDK, it didn't have something like raycast, which now we assume is part of the physics layer. And demos really did. I'm from Ireland. I have to throw a Father Ted reference in here. But most demos and games back in the day were cars smashing into boxes, Starsky and Hutch style. So you really did know that there was a rigid body physics simulation in your game if you saw a stack of boxes. Nowadays, of course, graphics representation has moved on quite significantly. Maybe even getting towards that single pixel per triangle. So we've got hardware acceleration on the graphics. I know it was tried on the physics, but let's not go there. We have hardware instancing, so we can obviously drive the number of creatures up. But things like instancing can't really be used for the physics simulation in the same way. So as a bit of an example, this is Just Cause 3. Our friends at Avalanche very kindly let me show you some of the background of this. Obviously, physically enabled barrels, constraints, and explosions. And there's lots of tricks nowadays for doing smoke and mirrors in our games. Not real smoke, not real, well, we're nearly getting at real mirrors. But this looks pretty. Rico is lovely. He's lovely animated. He's blended with his ragdoll. But actually, the physics representation is very different. So this is behind the scenes. This is the raw physics representation. It's a slightly different camera view. Rico's down in the bottom left. He's represented as a pencil shape. The blue lines, the blue cyan lines coming out are the view frustum from the player camera. But there's lots of obviously physics going on. I'm obviously biased, but I'd argue that everything critical about the gameplay, the physical representation, the sort of queries used by the game to get information off that representation, and obviously then the simulation, the update, are the gameplay critical elements here. The graphics, of course, sell you the experience, but you could argue that the physics representation is core, is critical to the gameplay. And as I already mentioned, we're halfway there towards raycast being back into the graphics engines. The early days, the raycast API was part of the graphics engine, and we're getting back there. But while the visual fidelity of something like our characters, something like our environments is getting massively different, what's the similar improvement on the physics side? I'm guessing we're probably still going to have capsules for a character representation, even though visually they're so much different. Okay, so let's dig into the physics engine a little bit more. A little bit of context, sort of stepping back a little bit. Physics, the scientific process could arguably be summed up in 3 words: describe, explain, and predict. So we have Isaac Newton describing and putting laws in place for our universe, and then the likes of Katherine Johnson using those laws to make predictions so that they can have real spaceships landing back in the sea correctly. Of course, I think that both have problems with the likes of Kerbal Space Program. Now, psychology is a little bit creepier. It adds in control into the end. A little bit of history in that, with abnormal psychology being the first thing that was started. But we obviously know that control is really important in our games as well. We can't just be relying on our physics simulation. Maybe today, Skinner would be doing horrible experiments with Souls-like games rather than the Skinner boxes. But if we look at the physics view of the game world, similarly, we're talking about describing it. We're talking about being able to query it. We're talking about being able to simulate it. And we're using the simulation is using the queries to update the description. It's doing it rather than your game logic doing it. But your game should also be able to use the same set of queries to make predictions. And also it should have control over the simulation. So there very much is a correlation between the psychology view of the scientific process and our needs in the game world. So the same fundamental physics representation that is going on in lots of different game types, the same physical fundamentals will be used in an arcade racer as a high-end hardcore simulator. The same underlying ragdoll simulation, for example, is being used, but it will look very different in Elden Ring or Skyrim compared to something like Uncharted or Spider-Man. It just depends on what level of control that the game developers are wanting to take away from the physics engine. They want to be able to ignore the physics altogether. So in terms of the physics engine, we should be describing, we should be querying, and we should be simulating. Let's look at how things have changed in each of those sections. So when we're talking about descriptions, already hinted at it, back in the day, box primitives, sphere primitives, very, very minor use of convex hulls for sort of hero pieces. And then the static world was static. It was maybe a polygon soup, but it may well actually have just been made up of box primitives as well. So static meshes, dynamic primitives, that's your world. You set your world up, don't touch it after that. And as we already hinted, we got a divergence between the physical and the graphical representations. And largely I'm talking about now here, rather than an axis-aligned bounding box or an object-aligned bounding box, the user-specified geometry where we can combine different primitives together to sort of balance between the performance and the quality of simulation for a particular object. We're now into sort of compounds of primitives, and we already talked about it with the barrel. Hopefully your physics proxy would be representative to your graphical object. But the important bit here is that the artists would actually be creating the physics proxy as well as the graphics representation. The coder would be doing all the bookkeeping of taking the transform from the physics simulation and applying it to the graphical representation. So there's a lot of manual work going on here. And behind the scenes in the SDK, there would have been code paths for specific combinations, box against box, sphere against sphere, sphere against box, lots of different code paths. And in particular, in the sort of PS2 area, we were very proud of our box-box optimization to the point that it was entirely used in adverts. And while it was used in our demos and we were actually advertising the cost of our 13-box ragdoll simulation for PS2, it was very much in the games at the time as well. I'm not sure if I should be saying this, but if you get the PC version of Max Payne 2, you can actually run the Havok visual debugger and have a look into the game. And this is what you get. The game very much uses boxes. Even the static world is made up of a bunch of boxes, very sort of select use of convex hulls in places. So is my mouse going to be which direction? Oh, hang on. I don't know which direction my mouse is. Is it down? Or somebody shout to see the mouse. Okay. So even though visually this is quite complicated, this table is simply just a box. And it's only in select places like the feet on this rolling monitor that would be using a convex hull. But the vast majority of the environment are boxes, even for things like cartons, and of course the ragdolls. This was great fun hooking up while somebody was playing it in the office at night over the network. You could hook up the VDB and have the ragdolls come to life again and just freak out the player. It's great fun. Of course, I talked about it being manual. Nowadays, physics engines are part of, I can't really see, but hands up who's using Unreal. Hands up who's using Unity. Hands up who's doing their own. I assume Godot's in there somewhere as well, is it? Oh, wow. Okay, cool. But nowadays, all that bookkeeping that I talked about, even the construction of the graphics representation is behind the scenes. So it's a tick a button to have simulate physics. Nowadays, I'm a little bit biased talking about Havok, but nowadays, rather than relying on all of these individual code paths, we're really just using convex hulls up the wazoo. Convex hull, shrink wrap around a point of cloud or a point cloud. But what we're actually doing is a little bit more, a Minkowski sum of that convex hull that we actually shrink and then apply an extra radius. Minkowski sum in this particular case then is a shrunken convex hull, and we're taking a sphere of a certain size and applying it within the entire space of that convex hull to give us the physical representation. That lets us get numerical tolerances, and it's much cleaner, especially in a stacking scenario. But it also means that we can have one single optimized code path rather than multiple code paths. It can all be automatic, so we're automatically shrinking, we're automatically simplifying, we're automatically creating these final collision surfaces that correlate precisely with the graphical representation that we're giving. And that shrunken convex hull plus a radius can give us all of the primitives. So 3 points, 3 vertices, and no convex radius gives us a triangle. 1 point, all convex radius, as we call it, gives us a sphere. 2 points plus radius gives us the implicit cylinder. And of course, you've got boxes and convex hulls and cylinders as well. So this is another VDB movie. Our screenshot from Skyrim. Everybody knows it's not. Starfield. The interesting thing here is that it's very much convex hulls. It's very much compounds of convex hulls. The saucepan needs to be a compound of convex hulls so you can put potatoes in it, which is clearly the main point of the game. We've got handles on our teapots. We've got lids. The geometry of the environment itself, not necessarily in this particular case, but it's vastly more improved. So we don't need to do any of this manual setup. We've got tools within the editor. Instead of a convex hull, we can get rid of that collision representation and automatically generate a convex decomposed representation based on X number of pieces. Manually, I'm clicking buttons here, but it doesn't need to be. You could set error tolerances and have all of this automatically generated. It means then whenever you're shooting the object, obviously if you were shooting boxes, then you can see the visual debugger on the left and obviously the Unreal Editor on the right. But it means now rather than hitting something that shouldn't be there, you can actually, this was harder than it looks to actually catch this video. But now you can be shooting under the table appropriately. So your level of detail can go up quite a lot. So I talked about primitives and we moved on to hulls as standard, and we're talking about compounds and them being the standard. But ultimately, we're talking about a more complex description, right? We can't have manual construction to get the correlation up. We need to have automatic setup and validation. I didn't talk about loads of things. I didn't talk about LODs. Even LODs are to a certain extent use case specific and based on a bit of bookkeeping. You know, our characters are capsules until we hit into them and turn them into ragdolls. That might go away at some point. Cloth is certainly a very manual process still. I'll hint on runtime hierarchical convex hulls in a minute, but now we're talking about convex hulls that can mutate, compounds that can mutate, breakable shapes. I didn't even touch really, apart from in the ragdolls, the description needed for constraints and for physical materials like mass and things. As I say, we're talking about describing more detailed worlds. In terms of the queries, I'm not necessarily going into this too much, but there's obviously a scale of complexity in terms of queries, overlap queries, box overlap queries, casting, whether we're doing a line segment query in the world, or maybe even casting a shape through the world. And actually now we can do rotation of a shape as it's being casted through the world. So if I've got my Viking game throwing my axe through the wall, I can actually have it spinning and correctly get the turn on the axe, rather than having to simulate it forward, find out where it hit, and then throw away all that wasted work. Next level up maybe is closest points, you know, 2 arbitrary shapes. What's the closest point between those 2 arbitrary shapes? And whenever you put a number of closest points together, you create a contact manifold. I'm going to be talking about contact manifolds a little bit more. They're mostly the important thing when it comes to performance. But if we look back at Max Payne, maybe there was n raycast between the character and the player. 1 raycast, that's the yellow one in the top right, for the camera to the player, so that the camera could move in or it could hide things that are in the way. and maybe there's an extra ray cast for the ground. Not very many, but now casts that used to be ray casts are now shape casts. We've got orders of magnitude more ray casts in the world, and we're dealing with bigger worlds, massive objects that need to be cast on, and objects that are really far away from the world. So you need to consider optimal pathways to get performance for your casts without getting the boiling effect that, if anybody remembers old cartoons like Rhubarb and Custard used to have. One example that I had was a simulation company was having to do parabolic raycasts. So they would have line segments for the massive parabolas. Too costly. They actually then just warped the geometry and had linear raycasts for it instead. So there's obviously ways around it, but we can't necessarily do that for the game, and double precision and handling large raycasts are important. Convex or contact manifolds, they're basically a shadow of one object on another object. These two boxes are obviously quite simple, but whenever it gets close enough, the green is our visual representation of the contact manifold. That's simple if it's a flat floor and two boxes. But if we've got compounds of compounds on detailed geometry, you can imagine the explosion of these contact manifolds. And when we're dealing with collisions, it used to be a simple on collision event. We can't do that anymore, just a simple collision with a simple sphere to trigger a sound. We've got so many events nowadays that we have to process that we've got entirely new approaches in terms of data streams that can be analyzed, multi-threaded, possibly deterministically. So while fundamentally the same algorithms are all in there, count has obviously increased, range has increased, complexity has increased, but on collection, on filtering, and on processing. So when we're talking about the simulation, just as a reminder, we're talking about the simulation using the query system to update the description, and our game needs to make predictions and control that simulation. And we're talking maybe about three areas: quality, performance, and quantity that we tend to test on a regular basis. We're always constantly testing each version of the SDK and indeed other SDKs out there. So we're always wanting to make sure our constraints are high quality, the collisions are high quality, and the performance is there for crazy destruction scenes. If I do a little then and now on quality, we used to have discrete collision detection. So we'd have bullet through paper problems. If we move bullet from time 1 to time 2, it might miss that collision unless it's a solid block it's hitting. And then when we sort of tacked on multi-threading, continuous collision detection, you get these massive performance spikes when you have to do a rollback and then sort of rerun the simulation. We don't have to do that anymore. By default, we've got a continuous collision detection system. We can expand the ABB of an object so that it includes its rotation and its linear velocity. And this, out of the box, gives us a general performance line that doesn't have those spikes. There are pros and cons of everything, of course, but we also then have mechanisms to deal with the cons. So it's a quality flag. You've got a baseline, which is a simpler, higher performance, smoother graph. And if there are certain areas where you hit potential cons and continuous collision detection, you want to have something that can handle that and only use the extra performance needed for those specific hero characters, for example. Contact manifolds used to be created point by point over a number of frames. So I don't know if you've played any old games and you walked into a room and there's been a stack of boxes and they've jittered a little bit. That was over a number of frames. The closest point was checked between this box and the floor, and one point was picked, caused a little bit of a rotation, and the next frame you'd pick up the closest point, which is now on the other side of the box, and a new contact point was picked. And over time, it would stabilize. So jittering was, or you would hide as someone comes into the room, you would run the simulation before they could see it. Of course, nowadays, we've already seen this clip where the contact manifolds are being created immediately. You don't have that jittering. I talked about shrinking convex hulls. I talked about numerical problems if you've got a box sitting on top of a box right at that edge. It used to be that we would have a collision tolerance, and it would actually make sure that the boxes were separated. So again, old games, you might walk into a room, you'll see a stack of boxes jittering, and then they'll hover slightly apart from each other. And that was this collision tolerance. But now, because we're shrinking the convex hull in a stack and adding this numerical buffer automatically as part of the construction setup, you don't have that visual gap anymore. You do, if you look at the visual debugger, you can see the visual gap. But all of our viewers, whenever we're looking at the collision representation, also let you add that convex radius as well. So you can see just the convex hull or the actual surface that is going to be used in the game. So when we turn off on that rounded surface we get from the extra convex radius, the gap disappears. Again, it's all automatic. You don't have to care. You just click the simulate physics button. Constraint performance and quality is also going up. Iterative solvers always have problems with mass ratios, long bridges, things landing on those bridges. We like to think our iterative solver is pretty good, but it's in certain cases not good enough. There's a poor little beggar here. He's got his quarter-ton block tied to his foot, dangling. And if you're dealing with an iterative solver, that's a mass ratio with one small hand holding up his body and a quarter of a ton tied to his foot. So you get the stretching, you get that sort of bouncing between two stable situations, which is the jittering in the hand. But nowadays, again, tick a button. You want the hero character to not stretch like that and be stoic. You turn on a different solver type and you get the performance. So we want quality by default, and extra sort of issues that can come up, like continuous collision technical and speculative contacts, we can have with optional extras. If we look at performance, back in the day, it was one world, it was single-threaded, and it really was like evolution. Multi-threading was bolted on top of that. So you didn't actually get a nice improvement as you increased the number of threads. It was pretty bad. Nowadays, of course, this should have been a big matrix. We've got single-threaded single worlds. We've got multi-threaded single worlds. We've got multi-threaded multi-worlds. All the combination is in there. So things like our visual debugger then, whenever we're connecting to Unreal, we've maybe got a world that's being used for the ragdoll and the animation blending, a world that's being used for setting up the static mesh, a world that's for the client, one for the server, one for the game window, one for the editor window. So there's multiple worlds, and we're having to deal with all of those multiple worlds. So multi-threading is the main crux now. It's not single-threaded if you don't want it to be. In order to make multi-threaded worlds updatable, currently we're using a double buffered world, which of course everybody will know in the graphic sense of a double buffer. So while one world can be simulating, you can be using the other world for queries. And then you can swap the two. So, a lot of work has been done in syncing between different representations, whether it's for this double buffering or whether it's for rollback or whether it's for network or whether it's for blending. There's a lot of different use cases for it. But ultimately, we're pushing towards a full thread-safe API so that the world can be queried and the description of the world can be updated whenever you like. So, we've moved on. We don't want single convex hulls on objects anymore. We want our chairs to be able to go under our tables. We want, all of our debris to be able to slide onto the table as well and actually sit on the chairs. So we've got our convex decomposition. We've got our tables under the chairs now. We've got our little objects falling on the chair and under the chair and looks great. But that big pile of blue objects there, they're full rigid bodies, right? They're landing on compounds. So we talked about compound horrors there. And a compound scenario where your compounds are colliding with compounds, the number of contact manifolds that we're generating could be massive. So I think actually this is coming in Chaos as well as Havok, but we're looking at hierarchical convex hulls as well now, so that you can have a level of detail on your simulation and only drill down to the very lowest levels if need be. And then the number of contact manifolds then can be reduced drastically, which means better performance. It also means less memory usage. But ultimately, performance by default is what we want with runtime heuristics, runtime rather than design time needs to ensure the performance limits. And then in terms of quantity, I love this little video. It's just showing how the world could be dynamic completely. We've got rigid bodies. I'm guessing there's actually a graphical effect as well in some of the rock slide. But if we try to do everything with rigid bodies, it could be really complex, as we've already seen. Niagara has got various options for like GPU SDF. The collision representation isn't necessarily great. We're not getting proper collision with the surface. It's probably some sort of point system, and it's actually against a pretty crude representation. There is also the CPU trace option, which gives a slightly better bouncing between the objects. Again, the objects themselves are just doing raycast really for the collision. And that also means that there's the potential for bullet through paper. Havok has got a sort of a middle ground. We're going to have to name them something different than particles because it's such an overloaded term. But here we've got stacking. We've got collision correct with the environment. We've got objects falling appropriately. But they're at least 5 times cheaper than a full rigid body. So, you know, we've got our good, cheap, fast triangle, whether you believe it or not. So something must be compromised. But for those Havok particles, we're dealing with only a single contact manifold with the full fat body. So you can imagine a corner case. Normally there'd be a wall at the back, at the side, on the floor. But these cheaper particles will only pick one of those, depending on what's closer. And then when they collide with each other, they're only colliding as spheres. So we're back almost to the beginning again with our sphere-sphere collision representation. But they're vastly good enough, and it's a lovely spectrum between full GPU debris flying around to good enough debris flying around to gameplay critical full-fat rigid bodies that are needed to not fall through the floor. So our particles, they're not perfect stacking, but they do fill up buckets, which is quite nice. And of course, you know, we can mix these systems together, and you know, the user might not even necessarily know which is which, if you know they're running around and shooting things anyway. So again, we're trying to push for quantity by default, and I didn't know how to sort of set the dietary options, low fat or full fat, to push that quantity. I want to touch briefly then at the end on the control element that is in psychology and also essential for the games. In the film space, you know, we've got our laws of physics, and they're all lovely, but the rule of cool overrides them. So that, you know, if it looks right, if Michael Bay wants it, it's going to happen. I don't know what the equivalent phrase in games. Maybe it is bring the fun, so the game designer should be able to decide. But ultimately, the physics engine is at your mercy. It shouldn't, we've seen it's encapsulating more complexity. It should inform when it can't deal with any scenarios that are impossible. But it also should be able to give you gracious defaults, or just completely go, it's up to you, man. Sort it out yourself. And one just example there, whenever we're talking about compound versus compound, we get into an entanglement scenario. Whenever we accidentally put a table right on top of another table that's both of them are compound, it's an impossible situation for a rigid body simulator to resolve. Every single pairing of those subparts are trying to resolve in a different direction, and you get a bit of a mess. Havok in particular is susceptible to this because it actually tries to solve the problem, and objects get stuck. Now, this is convoluted, but it actually can happen quite easily whenever you're dealing with compounds and you're dealing with destruction use cases. But we can analyze all the data, like the data streams, the contact manifold is in there. We can analyze them, see that all of these are combining together to give an entangled scenario and override that. So you're back into a quality simulation that would look like a convex hull, but you're dealing with a quality representation that's a compound table. That was lovely when I first saw the tables doing that, because I totally didn't expect it. So to sort of summarize, we want to push towards more automation on the physics representation. It's still using all the same things that everybody knows, but it's dealing with more stuff. We want to push towards design, push design decisions away and push it to the runtime. You know, you want to be able to tweak things rather than having to design it into your game. Coders then can worry about integrating all of these extra features or handling the specific use cases. And then the designers can worry about making sure that their ambitions can scale up. Now, I want to end on an example test that we did when we first were playing with nanite geometry to know how far we could push this. Physics, or Havok, while synonymous with physics, is really about dynamic environments and handling any sort of dynamic environment. So we wanted to be able to test what would be involved in a massive destruction scenario where we could block avenues off and have the AI get messed up, or we wanted to ensure particular pathways would stay open, and what would be involved in the storytelling narrative being kept while a massive avalanche is happening. So these are all the sort of initial tests that we were doing on a now that we've had an integration with a graphic engine where we could play with rather than our demo scenes, which programmer art is great. So things like this building, these are all full fat rigid bodies. This building, I don't think still looks good enough. I want the tower from Lord of the Rings, so we could add a ton more bodies in there. But when we do combine all of those effects together, we want the landscape to be completely destructible, so that, you know, we could add in our particles, our graphic particles, our sort of low-fat rigid bodies, our full-fat rigid bodies, so we can have truly dynamic worlds that do look great. And ultimately, you know, we'll have smoke and mirrors for real in our games. We've got ray tracing and physics matching. Okay, I will end it there.